Good afternoon, everyone. I assume you can hear me. Okay. Welcome to the last session of this course. The title is really short, Wrapup, and that means that I want to try to keep it short as well. As we speak, Xavier is hard at work in preparing the feedback for your third assignment. If I'm correct, I received the assignments, the second assignment from all of you, so I have also some work to do. So what I want to do today is give a short overview of all the topics that we discussed in order to establish what I expect you to know as we're going towards the oral exam, and then give you the rest of the afternoon time to start preparing or start working on the third assignment. That's the plan for today. So wrapping it up, I think if we look at the topics that we discussed during the class, then we can roughly split it into sections: fundamentals of biophotonics and applications of biophotonics or biomedical optics. So the important topics, and I'm going to run past each bullet point in the next few slides. The most important topics are absorption and scattering properties of particles and of tissues. The volume fraction dependence of these absorption and scattering properties. Monte Carlo simulations of light transport. Of course, you also made an assignment on that. The radiative transport equation and the diffusion approximation to that. And for this part, the materials consists of the slides, the book chapters in the book by Van Gemert, chapter 1, 2, and 3. That is that basically covers all these topics. And chapter number 5, which is on Monte Carlo simulations, only the parts that are about steady state. And then there is this document, Monte Carlo notes, but I guess you have already seen and used that for the Monte Carlo assignment. And then for the applications, we actually covered quite a lot of them. OCT, the most important one, I think. That's why it's in the top of the list. Vesicles and Rayleigh scattering is also on the top of the list, but because it also used kind of heavily the things that were discussed in the fundamentals. Raman spectroscopy from Johannes, elastic light scattering spectroscopy from Dick Sterenborg. Maurice talked about fluorescence and forensic applications. Marloes about higher harmonic spectroscopy, microscopy, and then last session was Xavier on instrumentation and specifically guided optics. For that part, for the application part, the materials are actually just the slides and the chapter 18 from Van Gemert's book, which is about OCT. All right. So let's just run through the fundamentals. I'm going to list a few things that I want you to be familiar with, that I want you to know, so we can have a short discussion about that during the oral exam. So I want you to know what the absorption efficiency is, what the absorption cross-section is, what the absorption coefficient is, how we interpreted it, what their units are, and how they are related with respect to each other. So this was basically the topic of the first class. So just to briefly reiterate, if we have a molecule, we can illuminate that with an intensity I0. Intensity has units of watt per square meter, and the molecule we assume can be assigned a geometrical cross-section G, which is then in square meters. The incident power on the molecule can then be calculated. That's the product of the intensity and the geometrical cross-section. So that is the incident power here. The absorbed power is whatever gets lost by through absorption by the molecule, and then with these two numbers, we define the absorption efficiency as the ratio of absorbed power and incident power. So it is a dimensionless number and simply tells you how efficient the molecule is in absorbing light. The rest of the light is just passed on. From that efficiency, starting with that unitless efficiency, if we multiply that with the geometrical cross-section, then we end up with an absorption cross-section. So that is you can interpret that kind of like the effective size that the light sees when it passes the particle. So that is a particle property as well. And if we have a bunch of these molecules in a solution, we could define an absorption coefficient, mu A, by multiplying with the number density. So rho is the number of particles, the number of molecules in this case per unit volume. So these are the three basic properties and how they are linked together. Of course, I would like you, once we know the absorption coefficient, we can use Beer's law to calculate absorption losses as light travels through a cuvette or through a tissue. I want you to be a little bit familiar with the absorption spectra of the important chromophores in biology. You've seen them in the first class and in the class of Dick and Maurice as well. Of course, the absorption spectrum of water is, of course, of great importance because most of our tissues are built up from water or are consistent of water, and it is also then that the absorption spectrum of water, the shape of it, and the dips and the peaks of it, mostly determine which wavelengths can be used to do measurements or to do treatments. Of course, the other major absorber is hemoglobin in its oxygenated or deoxygenated form, which is of course well known because it has these huge absorption peaks at visible wavelengths. For scattering, we actually use the same kind of formalism with efficiencies, cross sections, and coefficients, and their interpretation and their units are therefore also related. So the absorption or the scattering efficiency is then the ratio of scattered power over incident power. So the amount of power that is scattered away, the rest of the power just passes through unhindered. If we multiply the scattering cross section, the scattering efficiency with the geometrical cross section, we get the scattering cross section, but since we know that the incident power and the geometrical cross-section were also related, we can also make a different arrangement for that. So we can also write the scattering cross-section as the ratio of scattered power over input intensity. So I just want you to be familiar with these ways of writing it. Then for the scattering coefficient, we adopt a slightly more formal definition. Instead of writing it directly as the product of a number density and a scattering cross section, we can allow for the fact that we have multiple particles with different scattering cross sections. So then in that case, we generalize it a little bit. We define the scattering coefficient as the sum of all the scattering cross sections that are in the volume divided by the volume. So in that sense, it is kind of the density of total scattering cross section. Now, if all the particles are identical, then of course sigma, sigma of sigma s, that sum of sigma s will just be n times sigma s, and if n divided by the volume is rho again, then we have the same expression as for the absorption cross section. All right. One of the important characteristics of scattering is that it is size dependent. So the scattering strength and the direction in which light is scattered depends on particle size, and that is important because we have quite a large range of sizes in tissue, ranging from very small proteins, microtubules, to cells, or maybe even cell clusters that can scatter light. If we think of these very small particles, that the smallest scatterer possible is a dipole. And scattering by these very, very small particles behaves exactly as the scattering that we would see from such a dipole. Because this large range of particle sizes, there is also there are a couple of different scattering theories that can be used, and they are applicable only to certain size ranges, or they have other characteristics. So for the very small particles, for example, we have Rayleigh scattering that is only valid for particles that are much smaller than a wavelength. Then for particles that are much larger than a wavelength, we can use geometrical scattering, which usually has much simpler formulas. And for anything in between, if there if the particle is spherical, we can use mean theory. That is valid for all sizes, but it is only applicable to spherical particles, so that is a restriction in itself. Then these scattering theories have a set of inputs that we need to put in if we want to calculate scattering properties. So that I would also like you to know. To make that really specific, this is a graph of the scattering cross-section versus particle radius on the horizontal axis. And the three different theories that I just described are given in this graph. So in blue is Rayleigh scattering, which is valid only for the smaller particles. In red is the geometrical scattering, which is valid only for large particles. And in between the dots is the mean theory, which, as you can see, overlaps nicely with both regimes when just as long as the particles are spherical. Highlighted are the inputs, so what you need in order to use any of these theories to calculate. That's the size of the particle, the radius. It is the wavelength of the light, in this case 500 nanometers, and it is the refractive index of both the particle and of the medium in which the particle is suspended. Now this simulation has a rather high refractive index for the particle, 1.5. For tissue, it is generally a little bit lower, 1.4. And for the medium, since most of the tissues actually consist of water, we usually take the refractive index of water, which is about 1.3. So that works then. The other important property that describes scattering is the phase function. It describes the redistribution of scattered light over solid angle, over angles theta and phi, polar and azimuthal angle. The plot you see here is a polar plot. It only shows the polar scattering angle. And what we found is that for large particles, they will have a phase function that is peaked in the forward scattering direction, which means that most of the light scatters in the same way as where it came from, basically. It just continues on. And for a small particle, the scattering will be more isotropically, so it will be more or less equal in all directions. To parameterize this phase function, because using this function itself is not always that useful, we have the scattering anisotropy, which is defined as the average of the cosine of the scattering angle. And that means that if the average of the cosine is close to zero, that means that is close to zero. That means that if the average of the cosine is close to zero, that each angle is more or less equally probable. So that would be a small particle. If the scattering anisotropy factor is close to unity, that means that the angle is that angles will be close to zero, which means that light just propagates in the same direction. But you have been working with phase functions as well in the assignments, so that should be not much of a problem. Then there was the peculiarity that when we put particles in suspensions, then the scaling of these optical properties is not all that straightforward. So it is not always the case that if you just double the amount of molecules or double the amount of particles, that you will double the amount of scattered power or double the amount of absorbed power. We saw that for absorption in the first class, actually, and that effect was called absorption flattening or pigment packing. And it described the effect that if you have a certain number of molecules, you will measure a different absorption coefficient when these molecules are just floating freely in a solution compared to when these molecules are packed inside particles. So we kind of derived a ratio between these two absorption coefficients. So you see the equations over here. So in red is then highlighted in red is the absorption coefficient of a suspension. So that's the case when particles are really packed into, or the molecules are packed into particles, packed into red blood cells, for example. In blue is when the same amount of molecules would be present in a solution. So basically what you would get is when you take this volume of blood and you destroy the cells for the cell membranes with some method, and then the molecules would spread freely over the cuvette. Then you would measure the absorption coefficient highlighted in blue of the solution. And then if you and these are linked together by both the size of the particle, so that is the R, and by the absorption coefficient of the substance that was initially in the particles. So if you think of the red blood cell as a mini cuvette, then in green would be the absorption coefficient that you would measure just through that one red blood cell, just through that one cuvette. So there is three absorption coefficients in this equation, which makes it a little bit complicated. Then for scattering, arguably the situation was even more complicated because we had the effect there that if scatterers are placed in a medium randomly, then formally what we would have to do to calculate the scattered intensity or scattered power is to first calculate the electric field, which has an amplitude and a phase, add all these fields together, then square that to calculate the intensity. And from that we could calculate the optical properties. The problem lies with these phases. If you have a bunch of particles and there is on average no phase relation, then that will average out and then you can ignore it. Then you can just add intensities. But if you cannot ignore these phase differences, which is, for example, the case when particles are ordered in a volume, when there is a certain relation between their positions, then these phase differences cannot be cancelled, and that will work through in the optical properties. For example, in the scattering, in the total scattering cross-section of such a volume. That is accounted for by the so-called structure factor, which is a function that basically encapsulates all these interference effects, and the way to use it is shown in this formula over here. So, if you want to calculate the total scattering cross-section of a bunch of n particles, then you need to know some properties of the particles themselves. So, for example, this function S, which is related to the phase function. And this structure factor here, which you have to put into the integral and first do the product and then carry out the integration. You can write that as a function. If you want to write that in terms of the phase function, that is also possible. Then the total scattering cross-section is n times the scattering cross-section of a single particle, plus here with the green accolade, the factor that accounts for these interference effects. So if the structure factor is unity, which would be the case when there are no interferences, then the green part would just be an integral of the phase function, which would have to evaluate to unity because the phase function is normalized. If it is not, then we get a different effect. We can rewrite that, and that is then the second important formula for this part. We can write that also for the scattering coefficient, which was defined as the density of scattering cross-section. So we take the total scattering cross-section and divide it by volume. And in that case, we get the same scaling relation. So we get a scattering coefficient in case of interferences as a function of the scattering coefficient when we would neglect it, plus this correction term that accounts for the interferences. These interferences can be found, or you can understand how that works if we look at a bunch of particles and then look at the scattered field of let's say the eth particle. If all else is identical for the particles, then what is different is their position. So the Re over here in the denominator and the Re here in the phase term. So that tells you that if you have different particles at different positions, then these phases will be different and they will cause some interference effect. If the particles are truly randomly located, then usually it cancels out. But if there is a certain ordering, a certain structure in the sample, the most extreme case would be a crystal, where the scatterers are all at equal distances, then these interference effects will occur. There were two functions that that's fine. two functions that described this. So the structure factor was the one that we actually need in order to calculate the effect on the optical properties. The other function related to it was the pair correlation function, which actually described the organization of the sample. And these two were related through a Fourier transform relation. So it is, and in that way, that essentially cements that it is the positions of the particles that determine these effects. So the most important effect of this dependent scattering, this volume fraction dependent scattering, is shown in the red graph over here. Here's the scattering coefficient of a sample as a function of volume fraction. So the number of so along the horizontal axis, more and more particles are added. In the picture where these interferences are ignored, that's the blue curve. We see that it is just a linear scattering coefficient is just a linear function of volume fraction. So if you double the number of particles, then it appears that the scattering coefficient also doubles. But in effect, because these structure factors and pair correlation functions depend on the volume fraction, we see that in effect the increase is going to be sublinear, and we end up with some scattering coefficient that is actually much lower than what we would expect if it is not there. There is one nice biological example for this, and that is in the cornea and the hornflies. If you look microscopically at the cornea, then it's a very dense matrix of cells. If you would isolate one of these cells and you would calculate scattering properties from that, you would get quite a high number. And if you then account for the fact that there is a lot of cells in your cornea, then the scattering would actually turn out to be very high if you would follow the blue procedure. So high, in effect, that it wouldn't even be transparent. So light would not be able to reach the back of your eye, and you wouldn't actually see something. But the fact that these cells are very neatly positioned makes that we have to actually take into account this organization, and that lowers the scattering strength of the cornea, so light can pass through more easily, and hence we can actually see something. All right. Questions so far? Absorption and scattering. I've tried to indicate as much as possible in these slides where we actually discuss this. So okay. Well, Monte Carlo, there's a couple of things that I want you to know. The first is really the basic recipe, the basic principle. So if you want to simulate an effect, so let's say the effect is that the light is entering the tissue. You can't see my pointer. The light is entering tissue here and it is escaping there. Let's say you want to calculate the total probability of that happening. The recipe is then as follows. We can try to simulate as many possible photon paths that connect the entrance point to the exit point, and calculate the probability for each of that path happening. If these paths are all independent of each other, and they are, then we can add the probabilities to calculate the total event probability. And then in order to calculate the probability of one such a path, we break it down in sub-events. In this case, the sub-events are a propagation to site number 1, then a scattering at site number 1, then a change in direction towards number 2, then a propagation to site number 2, then again a scattering at site number 2, etc. We can calculate probabilities for each of these sub-events, and we are allowed to multiply these to obtain the total probability of this complete path, as long as they are uncorrelated, but that is what they are. So in terms of Monte Carlo simulations, that is then as follows: you simulate as many photon paths as you can, as your computer allows. Each of these paths is assigned a probability, and that probability is calculated by splitting each path in a sequence of propagations and scatterings. And then the propagations can be sampled using Lambert-Beer's law, step sizes, and then the scatterings. So the directions can be sampled from the phase function. part 2 and 3, but you did that in the assignment. So that is then the implementation assignment number 1. Well, there was a lot of terminology that went into this Monte Carlo simulation. So there are a couple of things that I think are good to know if we get to discuss this. So what is a probability density function and what is a cumulative distribution function? If you now have a probability density function, can you then calculate? Do you know how to calculate the expectation value from that? Then you should also know that the phase function is what's then called a joint probability density function for scattering angles. It describes the probability of scattering into angles theta and phi, with domains with theta from 0 to pi and phi from 0 to 2 pi. So that is the formal definition of the phase function. For Monte Carlo sampling, we don't sample it at once. We split the phase function into 2 marginal, so-called marginal probability density function, one for theta, one for phi. So how do we do that? What are the domains there? Apparently, I thought that calculating an expectation value is really important because it pops up again. And then finally, we define some probabilistic meaning of the scattering and absorption coefficient. So if I were to calculate the product of the scattering coefficient μs and a certain interval dx, what I'm then actually calculating is the probability of a scattering event happening in that small interval dx. Likewise, the product μa times dx is the probability of an absorption taking place in a small interval dx. And it also allowed us to define the mean free path. So the step size, basically, if you think back to the Monte Carlo simulation, the mean step size between scattering events as 1 over the scattering coefficient. Okay, and the final fundamental part was on transport and diffusion, so transport theory. So for that, there's a couple of radiometric quantities that went into that. So what is the intensity? What is the radiance, fluence rate, net flux, and directional fluxes? These were the most important ones, and their units. Specifically, the fluence rate has some physical importance. If you multiply, so the unit of fluence rate is watt per square meter, just like for power. And if you multiply the fluence rate with the scattering, with the absorption cross section, you're calculating something that has units of watts. So you calculate the amount of power that is absorbed. If you multiply the fluence rate with the absorption coefficient, you're actually calculating the amount of power that is absorbed per unit volume. And that's important if you want to do theory, for example. If you want to do damage, you need to know how much power you deliver, or the other way around. If you just want to do imaging or diagnostics and you don't want to do damage, then you have to make sure that your fluence rate is not too high. So the transport equation itself was a power balance of light flowing through the volume. So you can find that in the slides there, and I would like you to be able to identify the terms that go into that equation. So there are loss terms and gain terms, loss through divergence, loss through scattering, loss through absorption, and gain terms because light can also be scattered into the volume. Then one important result is that we found something a little bit in between, but it is nevertheless important, is a relation between a change in net flux going through a volume and fluence rate. So a flux is the net flux takes light going in one direction minus light going in another direction. The fluence rate is light actually going into all directions. And what this equation tells us that the change in net flux is proportional to the amount of light that actually goes through the volume, but it is also proportional to the absorption coefficient. So there is only one loss mechanism. So scattering just redirects light. It doesn't take away light. So scattering just when you have only scattering, then the amount of light is preserved. There is no loss. The only loss mechanism in here is absorption. So that is the only way to lose light. Another important result was was that you can have a subsurface buildup of fluence rate, because if you illuminate the surface, then just below the surface there are actually two contributions. One contribution is from the incident light itself, and another contribution is coming from deeper inside the tissue. That is light that has already entered the tissue, but that is part of that is now scattered back. So that means that below the surface you have actually more power available, more optical power available than the amount of power that you're putting in at that moment. And that is also something that that needs to be taken into account if you want to do therapy or diagnostics subsurface. Then the diffusion approximation was discussed in this movie. There are the important things that I would like you to know there is that there's an expression for Fick's law of diffusion, but then applied to photon transport. So it is again in terms of net flux and fluence rate. Along the way, yet another coefficient was defined, a reduced scattering coefficient. It is defined as the symbol is mu is prime, so there is a little prime on there. It's equal to the scattering coefficient times 1 minus the anisotropy. And the physical interpretation of that was that you can make an equivalence between a scattering process which takes many small steps with very small scattering angles, so very slow deviation from incident direction. So equivalently, if you trace such a photon long enough, then you can supplant that or replace that with scatterings that take larger steps and scatter over larger angles. So that is then equivalent, and that is basically what the reduced scattering coefficient describes. The funny thing is that in the diffusion approximation, the scattering coefficient itself does not appear anymore. It appears only in the form of the scattering of the reduced scattering coefficient. So that also, Fick's law is a real diffusion equation. So it has a diffusion coefficient. So there is also an optical diffusion coefficient, and that is related to that reduced scattering coefficient by this relation. So the diffusion coefficient is 1/3 times the reduced scattering coefficient. Perhaps the most important thing to remember going forward is that the diffusion approximation is quite limited. So the transport equation is exact, but very difficult to handle because you have all these variables. So it's difficult to solve. The diffusion approximation is in essence much simpler, but because there is this underlying assumption that it is a diffusive process, it means that it is not really valid if you're very near the light source or if you're very near a boundary in tissue. So take that into account. Okay, so far for the fundamentals. Any questions? All right, then I'll briefly go through the applications and also what I think is important to do there. So this one is a little bit an odd one out because it also had a lot of applications of Rayleigh scattering and meteorite, so that is important. The concept of a flow cytometer was discussed, and you calculated. You did that in assignment 2 as well. In Edwin's class, you calculated how you can determine how much power is picked up by an optical system if you know the phase function and if you know the characteristics of the collection optics. If you know the acceptance angles, then you know how to. Then you can integrate the phase function over these angles and then determine how much light is captured by the system. Then OCT was a pretty big chunk of the class as well. So there's a little bit more items that are important. One is of course the concept of low coherence and of interferometry. So it is usually Michelson interferometer that uses a broadband light source, and the consequence of using a broadband light source is that an interference pattern will appear only at a very small position in space. So if you would elongate one arm of this interferometer, then you will only see an interference pattern at a very small specific set of path length differences or mirror positions of that interferometer. And the principle in OCT is then to turn it around, say that if I see an interference pattern and I know the length of one arm, then I can calculate the length of the other one, and I know where my reflection came from. So that is basically the signal formation. Also, the equations Johannes went through with you show that in the end, the part that contains the signal, so the part that contains the scattered light from the sample, is multiplied with the intensity coming from the reference arm. So that means that the great benefit of OCT is that the reference arm actually works kind of as an amplifier of a very weak optical signal coming from the sample. Of course, such a system has resolutions, axial lateral resolutions, so axial in depth and lateral in the plane. The axial resolution is determined by the coherence length, by the light source, and the lateral resolution is determined by the optics, by the diameter of the beam. Then we had two different, or three different, if you like, implementations of OCT time domain. The old-fashioned one, where a mirror is actually moved back and forth. That was pretty slow. And then the spectral domain OCT, or Fourier domain OCT, or OFDI, optical frequency domain imaging, all terms for the same thing, is much faster because now the mirror is not moved anymore and the spectrum is detected at once using a spectrometer. So that can be much faster and is more sensitive. That was that could be proven by looking at a signal to noise analysis. So by looking at all the noise terms that can occur in an OCT system, it was possible to show that a spectral domain system has a better signal to noise ratio, better sensitivity. So the important things here is that an ideal OCT system, and of course we assume that they are all ideal, is so-called shot noise limited. So that is the important noise to know about. So I'd like you to know what shot noise is. And then finally, going to some applications, to some use cases of that. So, I would like you to know what common OCT wavelengths are. So basically, these are 800 nanometers and 1300 nanometers these days. So for what application would you choose such a wavelength? So that means comparing 800 to 1300 nanometers, we know that the scattering is a little bit stronger at 800 nanometer, but the absorption is a little bit lower compared to 1300. So that is a trade-off. And for certain tissue types like the eye, the trade-off works in the benefit of 800 nanometers. For other tissue types like skin, it works in the benefit of 1300 nanometers. So that is then the goal. Raman, also Johannes' class. I'd like you to know what the difference is between Raman activity and infrared activity of a molecule. I'd like you to be able to reproduce the Jablonski diagram for the different Raman approaches. We had Johannes discussed a couple of them. Most importantly, the difference between Stokes and anti-Stokes Raman. So the difference in terms of Jablonski diagram, but also in terms of what actually happens in the molecule. I'd like you to use that I'll just call it the Raman shift equation. I'm not sure what the correct term is, but that equation that allows you to calculate a Raman shift or an excitation wavelength or an emission wavelength, if one of the three, if you know the other two. I'd like to have some ballpark numbers about what the efficiency of the Raman process is. The spoiler is it is really inefficient, so only one in a billion photons or so actually gets Raman scattered, so it is very inefficient. And some use cases. You may have encountered these already when you're making assignment 3. I don't know that yet, but that could be. Then Dick's class on elastic scattering spectroscopy. That was basically a very big application of the things we studied already in the fundamentals. So it related to absorption and scattering properties. It related to Monte Carlo simulations, to the diffusion approximation. So that's then a great overview of the applications. So when is this technique used? Where can you use it for? Is it used for diagnosis or for monitoring? And finally, DIRK also introduced as a relatively new technique, hyperspectral imaging. I think Maurice also talked about that later. Then for Maurice, fluorescence, same thing as for Raman. So the Jablonski diagram and the physical principle for fluorescence. Again, use cases for fluorescence. Why? When? What can you do with it? When would you use it? What is the? When is it beneficial? When it isn't? Maurice also talked about photodynamic therapy. So there too, the Jablonski diagram and the physical principle. It's a little bit more complicated because it needs two molecules where energy transfer takes place, and also when you use it, what are the benefits? What are the drawbacks? So we can have a qualitative discussion about these techniques. Then Marloes talked about the higher harmonic microscopy. That gave way again to a few technical discussions as well about resolution in microscopy, the numerical aperture of a microscope objective. It had some fundamentals in nonlinear optics. I'm not going to ask too much about that, but I would like you to know to at least have the basic principle, to study the basic principle. And then there were again a few Jablonski diagrams for the various multiphoton techniques. 2-photon and 3-photon fluorescence, for example, and again, what can you do with it? Why would you use it, and what would be the benefit? What would be a drawback? Then I'm skipping Chavez class because you're working on that now, so not going to ask anything specific about that. The last remark that I want to make, and this is also for logistics, is the oral exam that will take about 20 minutes. Certainly not longer than that. And I will try to center my questions around the assignment that you're making now, around assignment 3. So you'll pick a technique or a few techniques to solve your clinical problem, and I'll try to center my questions a little bit around that, not entirely, but so then at least you know where you can expect the focus to lie a little bit. It will likely feature a small calculation, not too long, so something like calculating the Raman shift or calculating the resolution of an OCT system, for example. Then that is basically all I have to say about what you're supposed to do. The materials were on the first slide. There is I posted along the way. I posted some research papers and other materials on Canvas as well. Of course, you're free to read everything you like to read, but the thing that I'm going to ask questions about are in these, just in the things that are listed in these slides. This presentation. The logistics of the oral is a little bit challenging because we have 21 students. So my proposal is, if some of you are feeling up to it, to have a couple of exams already at Thursday, because otherwise I can't fit everything on Friday, I'm afraid. So what I would like you to do, I'll post this short. I'll put this short thing in an assignment as well, in an announcement as well. Is for you all to send me an email with your preferred time slots. So let's say 3 time slots that you prefer, and then I'll try to cook up a schedule from that proposal, and then hopefully we can fit it all in these days. If you want, if you want another day than these two, also let me know, because I'll try to be as flexible as possible to fit it all. So just let me know what your preference is. That's the end for me for today, and also for the course, I'm afraid. Let me at least take the opportunity to thank you all. I think I'm very glad that everybody attended all the lectures in such good numbers. I'm very happy about that. I hope you enjoyed it. It's still this is the second time now that the course is given completely online. It is still takes a little bit of getting used to. So well, for all of us, I hope that we can have soon enough some face-to-face classes again. But well, we'll have to see.
Well, thank you, DIRK, because it must have been so hard to give a lecture online. So my compliments. Thank you very much.
Okay, in that case, I think Xavier is, like I said, is working really hard to give you feedback on your assignments. I'll be online all day, at least, and also in the coming days as well. So if you have any questions about anything, do not hesitate to shoot me an email. I will answer you as fast as I can. All right, thank you very much, and then I'll see you next week, somewhere next week.
Okay.
Bye.
Next week.
Bye.
Dankjewel. Doei.
Bye.